Welcome to the lecture series of Abstract Algebra, Part 2 of Module 1. It's me, Dr. Shahida at MES Mampad College. Today we are going to discuss about different types of binary operations and isomorphic binary structures. In the Part 1 of this lecture series, we already discussed about what is a binary operation and the related examples. So, here we consider the first category of binary operation, which is commutative. That is a commutative binary operation. A set S and an operation star. Star is said to be a commutative binary operation in S if A star B is equal to B star A for every A comma B belongs to X. For example, if we consider the set of all real numbers, addition is a binary operation on R. Also, A plus B is equal to B plus A for all A B belongs to R, which implies addition is a commutative binary operation in R. Similar way, we can see that if we take any two elements A comma B belongs to R, then AB is equal to BA. Means multiplication is also a commutative binary operation in R. Next type of operation is associative binary operation. A binary operation star on a set S is called associative if A star B star C is equal to A star B star C for every A comma B comma C belongs to S. That is, for example, if we consider the set of all real number, already we see that addition is a commutative binary operation. Now here we can easily show that A plus B plus C is equal to A plus B plus C for every A B C belongs to R. Means addition is a associative binary operation in R. Similar way, we can easily see that multiplication is also associative binary operation in R. That is, AB into C is equal to A into BC for all ABC belongs to R. Think about in the part 1 problem 3, we already discussed about addition modulo n operation in the set Zn, where Zn is equal to set of all 0, 1, 2, 3 etc. n minus 1. That is, Zn contain n elements. And the operation modulo n means if we take any two elements A and B in Zn, then A plus modulo n B means adding two element A plus B and dividing by n, we consider only the least positive remainder. So in the problem 3, that is we already discussed in the part 1, that is the problem is like that Z6 addition modulo 6. Using the table, we already drawn a table there. Using that table, we check whether the given binary operation is commutative or not. And the second question is check whether subtraction is a binary operation in the set of all real numbers. We already seen that addition, multiplication are associative and commutative binary operation in set of all real number. Here third thing is binary operation with identity element. That is an operation, a binary operation star on a set is said to be a binary operation with identity element if there exists an element E in S such that A star E is equal to A is equal to E star A for all A belongs to S. The element if it exists is called the identity element of the set S under the binary operation star. For example, if we consider the set of all real numbers or set of all rational numbers or set of all integers, 0 is the identity element of the binary operation addition. That is, if we take any element A, then 0 plus A is equal to A plus 0. So 0 is considering as the additive identity in the set of all real numbers or set of all rational numbers or in set of all integers. Similar way, 1 is considered as the multiplicative identity in the set of all real numbers, set of all rational numbers or set of all integers. Think about the binary operation plus on Z plus has no identity element. Why? Here is a theorem, associativity of composition. The statement is like this: let S be a set and F, G and H be functions mapping S onto S. Then F composition G composition H is equal to F composition G composition H. That is, we want to prove that LHS is equal to RHS. For that, we consider f composition g composition h of x is equal to, by the property of composition, that's equal to f of g composition h of x, that's equal to f of g of h of x. And the second part, that is the right part, f composition g composition h of x is equal to f composition g of h of x, that's equal to f of g of h of x. From these two lines, we can easily verify that f composition g composition h is equal to f composition g composition h. That is, function composition is an associative property. Second theorem is uniqueness of identity element. That is, let S be a non-empty set and star be a binary operation with identity on S. Then the corresponding identity element is unique. That is, if S is a set with a binary operation star, if the identity element E exists, that must be unique. So we want to prove this using the method of contradiction. That is possible assume that there exists more than one identity element and reach a contradiction. So the proof is like this. Since star is a binary operation with identity on the non-empty set S, then there exists an identity element E belongs to such that A star E is equal to A is equal to E star A for all A belongs to S. Now we suppose that there exists another element E dash which satisfies the same property. That is, A star E dash is equal to A is equal to E dash star A for every A belongs to S. Then regarding first E is the identity, then what happened? E star E dash is equal to E dash. Now we are taking E dash is the identity, then we get E star E dash is equal to E. From these two sentences, it is easy to easily verify that E is equal to E dash, showing that the identity element must be unique. Now going through the concept algebraic structure. A non-empty set S together with a binary operation star on S denoted by S star is called a binary structure or binary algebraic structure. For example, we already discussed lot of binary structures like R plus, Q plus, Z plus, etc. Here also R with the two binary operations like R plus dot, Q plus dot, Z plus dot, R, etc. are binary structures. Isomorphic binary structures. Two binary structures is said to be isomorphic. That is, here we consider S star and S dash star dash. It satisfies following properties. There is an isomorphism from S to S dash which is 1 1 and on 2, and which satisfy the homomorphism property. That is, let S star and S dash star dash be two binary structures. An isomorphism of S with S dash is a one-to-one function mapping S onto S dash such that phi of S star Y is equal to phi of X star dash phi of Y for all X comma Y belongs to S. If such a map phi exists, then S and S dash are isomorphic binary structures, and which is denoted by the symbol. Here star is a binary operation on S and star dash is the binary operation in S dash. For example, if we consider two tables given below, here S star is a binary structure. S is the set containing the elements A, B, C, and T be the set containing the elements 1, 2, 3. Define a phi from S star to T star dash by phi of A is equal to 1, phi of B is equal to 2, and phi of C is equal to 3. Then phi is a isomorphism and S star and T star dash are isomorphic binary structures because it also satisfies the homomorphism property. That is the property phi of A star B is equal to phi of A star dash phi of B. To show that two binary structures are isomorphic, we have to proceed as follows. There are few steps. First step says that we can define a function phi that gives an isomorphism of S with S dash. And the second thing is phi is a 1-1 function. Third is that phi must be onto. Finally, it satisfies the homomorphism property. Phi of X star Y is equal to phi of X star dash phi of y for all x by belongs to S. Here is a problem. Show that the binary structures R plus, where plus is usual addition, is isomorphic to the binary structure R plus dot, where is a usual multiplication, and R plus is the set of all positive real numbers. That is, here we want to find an isomorphism phi from R plus to R plus dot. So we can define a function phi from R to R plus by phi of x is equal to e raised to x. Now we want to prove that this map phi is 1 1 onto and phi satisfy the homomorphism property. To prove phi is 1 1, we take two elements in R plus, and I assume that phi of x is equal to phi of y, which implies e raised to x is equal to e raised to y. Taking logarithm on both sides, we get log e raised to x is equal to log e raised to y, which implies x is equal to y. Therefore, phi is 1 1, because if we take two images are equal, then their pre-images is equal for any x comma y belongs to R. Therefore, phi is 1 1. Next, we want to prove that phi is onto. For that, choose any R belongs to R plus. Then log R belongs to R, and phi of log R is equal to e raised to log R, that's equal to R. Hence, phi is onto. Thus, phi is a 1 1 onto map. It is remained to prove that phi is a homomorphism. For that, we take any two elements x comma y belongs to R. Then phi of x plus y is equal to e raised to x plus y, that's equal to e raised to x into e raised to y, that's equal to phi of x dot phi of y. Therefore, phi satisfies the homomorphism property and hence is a isomorphism. Therefore, we prove that phi from R to R dash is an isomorphism. Thank you for watching this part. We can see soon for the next part. Thank you.